Alrighty, today's lesson is 2.2, which is graphs of quadratic functions. Now we've already seen the parent graph for quadratics, but today we're just going to focus a little bit more on the different types of equations that quadratics can come in. So the first form right here is called the standard form, and this is what we see when we work with the quadratic formula when things are multiplied out. If you want to find the vertex of this type of form, you're going to do the opposite of b over 2a to find your x-coordinate, and then you're going to plug that in to your equation to find your y-coordinate. The axis of symmetry is a vertical line that divides the parabola in half, and so since the vertex is in the middle of the base of the parabola, then to find the equation for that line, you're going to write x equals the opposite of b over 2a. And again, you're going to want to make sure that you put that x equals because it is a vertical line. The next form of a quadratic equation looks like this. This is the one that we're used to seeing. This is like the vertex form. On this one right here, you can write that this is also vertex form. This one right here, the vertex is going to be hk, and the axis of symmetry is just going to be x equals h because this one right here is already in vertex form. If you wanted to take this one from vertex form into standard form, you would just multiply it out. Couple of other definitions that we already know. We know the minimum is the lowest point of the parabola, so it's going to be the y value of the vertex. We can find that in the graphing calculator or just doing it by hand by calculating the vertex. The maximum is the highest point of the parabola if it's opening down, and again that's the y value of the vertex. The x-intercepts, we already know this definition. That's where the graph crosses the x-axis, and so they're also called zeros or roots. And the y-coordinate is always equal to 0, and to find that we have to set the equation equal to 0 and solve. The y-intercept is where the graph crosses the y-axis, and that x-coordinate is always equal to 0, and to find it you're going to plug in for x and simplify. Note, we're just going to draw some little things down here just so we're clear on this. If the graph of the parabola opens up, like for example this parabola here, then the leading coefficient, which is a, is going to be greater than 0. And some of the key points on this one would be right here. These are the zeros or the x-intercept, but notice just the way that I had drawn it, that just happens to be an x and y-intercept because it goes through the origin. That's an x-intercept. This right here is going to be a minimum, and we're going to find that minimum using the y value of the vertex. So it's at the y value of the vertex. And let's hypothetically say we had another one over here. This one, our leading coefficient, or a, is going to be less than 0, which means it's going to be opening down. This one is going to have a maximum at the y value of the vertex. But notice this one doesn't have any x-intercepts or zeros because it's not crossing the x-axis. And even though we don't see it cross the y-axis though, somewhere down off the page it would have a y-intercept. This little bullet point right here is important for you guys. You need to make sure that for this class you use at least 5 points when graphing a parabola. So you can either use an xy table, use intercepts and vertex, or use the transformations that we learned in 1.6. So we're going to jump around with our examples a little bit just because I want to. So the first one we're going to start with is example 2. And it says to find the x and y intercepts of the function. So if you forget how to do that, you have it over here on the left-hand side. So to find your x-intercepts, those are the zeros, you are going to set the function equal to 0 and solve it. So you might think that you need to FOIL that out, but you don't need to. Just subtract the 1 from the other side. Whatever I'm solving for, I keep on the left, so I'm going to write it like this. And then you're going to square root both sides. And you might be getting a little red flag right here, but it's okay. You're going to get x plus 3 equals plus or minus I. And then when we finalize that, we get negative 3 plus or minus I. This just means that if we were to graph this parabola right here, it wouldn't have any x-intercepts. And if you kind of look at this right here, this parabola is going left 3 and up 1. So if we just drew a basic sketch, left 3, up 1, its vertex is above the x-axis. So of course it's going to not have any x-intercepts. The y-intercept, we need to plug in 0. So you're going to do f of 0. We want to find out how the y value, how it changes on the y-axis. So 3 squared plus 1 is 10, so that's the 0.010. So here are here's the y-intercept, and then here would be the x-intercept, even though it doesn't have one on a Cartesian plane. Okay, so now we're going to go ahead and move on to example 3. You have this form right here, which is the first form up on the paper up here. So you can see it's been multiplied out and it's in term form. So in order to find the vertex of that one right there, give you a little space down here to do it. You're going to do the opposite of b over 2a to find the x-coordinate, and then you have to plug in the x-coordinate to get the y-coordinate. So this is the same thing as what I just said, but in fancy notation. So take whatever you get from here and plug it into your function to get your y-coordinate. So when we do that, we take the opposite of b, which is 4, so negative 4 over 2a, so that would be 2 times negative 1. Negative 4 divided by negative 2 is 2. And then to find the y-coordinate of our vertex, we are going to go f of 2, which is going to be negative 2 squared plus 4 times 2 plus 1, which is going to be equal to 5. So our vertex is 2, 5. And what's really cool about the vertex, it's a really key feature in this graph of a parabola, is it's going to tell us a lot about the graph. So first of all, the axis of symmetry, it's going to go right through the vertex and it's a vertical line, so it's x equals 2. It's always x equals and then whatever your x-coordinate of your vertex is. Now, because this graph has a negative leading coefficient, or a is negative, it's going to have a maximum, and the maximum value is going to be the y value. So what's the highest point on this graph? It's going to be 5. And if you want, you can write when x equals 2, but it doesn't ask you that. And then the zeros of this function we don't have from the equation, but we can find them. Zeros are the same thing as x-intercepts. And this one's going to be a little bit crazy just because of the function. So you can use quadratic formula to solve this, but it's much faster if I use completing the square, and it's a good review. So I'm going to get that to be a positive x squared. And the way that I can do that is I can multiply both sides by negative 1. So I'm switching the sides just for help here for ease, but this would be minus 4x plus blank. And then this would be negative 1, but I have to switch it to the other side, so I get 1 plus blank. And then I'm going to complete the square on that. So what makes that a perfect square trinomial? It would be 4. 1 plus 4 is 5, and then it's just so much easier to do the square root here. So square root, x minus 2 equals plus or minus root 5, x equals 2 plus or minus root 5. So with equations like this, you might not always have a nice clean x-intercept, but that's okay because we know how to approximate. So this is 2 plus or minus And square root of 5 is in between the square root of 4 and the square root of 9, so it's closer to 4. So if we were to take the square root of 4, it would be 2. It's a little bit bigger than that, so we'll say 2.1. So this would be 2 plus 2.1, which would be 4.1, so like here, up on our graph, and 2 minus 2.1, which would be negative 0.1, so that would be like here on our graph right there. So when you go to write your zeros, you're going to go to plus or minus root 5 comma 0. We use the decimal approximation to graph, but not when we actually write the exact value of the 0. The y-intercept is really easy. It's just going to be f of 0. So you plug in 0 to your equation here, and the first two terms have x's, so they become 0 plus 1 is 1. So that's what we have. F of 0 is 1. So that goes right here. And the really cool thing that we haven't really touched on that much is that axis of symmetry. And so right now you can see we only have 4 points, 1, 2, 3, 4, and I told you you needed 5 points on a parabola. And so where do we get that 5th point from? Well, if you look at the y-intercept, it's 2 units away from the axis of symmetry, so you're guaranteed another point on the other side. So you can just use the axis of symmetry as a reflection point. And then this is the graph that you get right there. Okay, so let's go up to example 1, which is this graph right here. So with that, I'm going to change the focus here so it doesn't keep going in and out. Okay, hopefully it locks it there. Okay, so this example right here is going to be about the vertex form. How do I know it's in vertex form? Because I see parentheses. We could graph this the way we learned in 1.6, which is how I'm going to do it. But there's other ways to do it too. You can make a table and go from there. So the table is something you can always fall back on if you need it. So what I want to point out here is in our order of graphing with transformations, we have a vertical stretch by 2. We have a reflection about the x-axis because it's out in front. And then if we set that equal to 0, we see we're going to go right 3 and up 8. So right 3, up 8. Well, the other thing that you can see right from this right here is this in vertex form. The x-coordinate of your vertex is in with your x, but you're doing the opposite. And then the k, you don't do the opposite because functions are solved for y, and since that's the y-coordinate, you get to take it right there. So over here on this one, the vertex is going to be 3, 8. Remember, if we know the vertex, we know two other things. We know that the axis of symmetry is x equals the x-coordinate because it divides it in half. And then this graph, because it has a negative in front, is also going to have a maximum because it's going to be opening down, and it's going to have a maximum value of 8 when x equals 3. If you want to know your x-intercepts, you are going to set the equation equal to 0. Like that. And solve this equation. So again, don't worry about foiling it out, just undo the stuff around the x. So the first thing I would do would be to move the 8 to the other side, and again, because I'm solving for x, I've switched the sides. Then divide by -2, so then that gives me x minus 3 squared equals 4. Square root both sides. X minus 3 equals plus or minus 2. So this is a nice perfect square, so it simplifies to 2, so we get x equals 3 plus or minus 2. So don't ever leave it like this. This can be simplified. This one down here with the plus or minus, could not be simplified because it has a radical, and that's why we left it. But something like 3 plus 2 is 5, and 3 minus 2 is 1. So our x-intercepts are 5, 0, and 1, 0. And then our y-intercept, don't be tempted to just say it's 8 because it's not in the same form as this one right here. So to find your y-intercept, you have to plug in 0. So when we plug in 0 to this equation, 0 minus 3 is negative 3. Negative 3 squared is 9, times negative 2 is negative 18, plus 8 is negative 10. So when all is said and done, I go 3, 8, that's that point up there, and then I have 5, 0, 1, 0, and way down here, 2 more down, I have negative 10, 0. So there's my 4 points. I need 1 more point, so we're going to use this y-intercept in the axis of symmetry to reflect it over, and then it's going to come down like that, and there's our parabola. So if I had graphed it using transformations, I just want to show you guys real quick, this is how I would have done it. So I would have plotted just the x squared points because it's my parent function, and I would have gotten those points right there. And then we always take care of our stretching first, so it has to stretch by 2. This one doesn't stretch, this one goes up here, here, and then this one's 4 away, so it goes all the way up to 8. So the purple points are the stretched points. And then from there, I need to reflect it. So if I take those purple points and reflect them, I'm going to get these pink points right here. And then my last graph is going to be to move it right 3 and up 8. So if I move all these points right 3 and up 8, I'll get the graph in blue that I have. So again, this teal colored graph, turquoise colored graph is y equals x squared. The purple one is when I stretch it by 2. The pink one is when I take that stretch graph and reflect it. And then the actual navy blue graph is right 3 up 8. Okay, so that's the first 3 examples. We're going to look at example 4 now, which is just really hitting home with whether a parabola has a maximum or a minimum. So does this function have a maximum or minimum? It all depends on how it's opening. Because this has a negative, it's opening down, so that means that that graph will have a maximum. Find the value of the maximum or the minimum. Well, in order to do that, we have to do the opposite of b over 2a because it's in standard form, not vertex form. But we have to be really sure and really careful that we actually find the y-coordinate of the vertex because that's the actual maximum or minimum. It's not the x-coordinate. So the opposite of b would be opposite of negative 12. Which would be positive 12 over 2a. So the opposite of b would be 12. We already talked about that. Divided by negative 4. So that's negative 3. So that is my x-coordinate. Now I need to do f of negative 3, which will be negative 2 times negative 3 squared minus 12 times negative 3 plus 3. So just be careful and make sure that you follow order of operations. So negative 3 squared is 9 times negative 2 is negative 18 plus 12 times negative 3 is 36, and then plus 3, so that's, what is that, 39 minus 18, which would be 21. So this one has a maximum of 21. And then here's something that's interesting is we're throwing in the domain and range into this problem. So when we go to do the domain, we're just drawing back from that 1.7, 1.3a lesson where we look at the equation and we say, is there a denominator or is there a square root? No. So by default, its domain is all real numbers. Now when we go to do the range, we need to consider this maximum point. There is a highest point at 21, so that is going to be from negative infinity to 21, and it can include 21, so we'll do a bracket. Alrighty, go ahead and flip it over. You might have to pause. I'll let you guys see that one. Okay, so for example 5, this is the one that we've been working on. It says, among all pairs of numbers whose difference is 8, find a pair whose product is as small as possible, and what is that minimum product? So, it might not look like the one we've been doing, but we'll actually do that in example 6 in just a second. So just like we did before, find a pair whose product is as small as possible. So that's what you're being asked for. So we have to recall that product just means multiplying. And since we're dealing with two numbers, I'll call the first number x and the second number y. Then with that first sentence, we're going to write another equation. Among all pairs of numbers whose difference is 8. So when I subtract these, I get 8. And then from there, I come down to this quadrant, and I'm going to solve for y. So I move the x to the other side, and then divide everything by -1. So I get x minus 8. So now I'm going to come up here and plug this in. So I get p of x equals x times x minus 8. I can change it to p of x, which is function notation, because once I substitute this y in, the right side has all x's, so it's the product in terms of x. And then so that I can finish out this problem, I'm going to distribute. Now, notice the question says, what is the minimum product? And also notice we have a parabola here. And this parabola is opening up because A is positive. It's +1. So that means that this graph is going to have a vertex and it's going to have a minimum because it's opening up. So if I find the y-coordinate of the minimum, then I will be able to find the minimum product. So this is the way it works. We're actually going to be finding the pairs of numbers and the product. So I'm going to do the opposite of b over 2a because that's going to give me x. Now x is one of the dimensions here, or I'm sorry, not one of the dimensions. X is one of the numbers. So to find it, I'm just going to take the opposite of b over 2 times a. So that gives me 8 divided by 2 is 4. So because this is the x-coordinate of the vertex, the x value, or one of the numbers, is 4. Now this question is asking you for the minimum product. So because it's asking you for the minimum product, you can take this 4 and plug it in. And because that's the product function, it'll give you what the minimum product is. So the minimum product is -16. Well, what's the other number then? So if we have x equals 4 and we know the product is -16 because we plugged it into the product function, then what would be the other number? Well, you have two choices. You can either go -16 divided by 4 using the product equation, or you can come over to this, because this is the other number, y is representing the other number, you can just plug in 4 minus 8, so y equals -4. So the three things we have x is equal to 4, y is equal to -4, and the product, the minimum product that we have, is 16. So your hint on these problems is going to be that it says minimum product. So example 6 is our final example. This one right here says you have 200 feet of fencing to enclose a rectangular region. Find the dimensions of the rectangle that maximize the area. What is the maximum area? So you guys know we've been practicing this problem for a while. This is the end of it after this lesson. So you have 120 feet of fencing to enclose a rectangular region, so that's talking about our perimeter. Find the dimensions of the rectangle that maximize the area. So here I go area equals x times y. Over here, there's no funny dimensions, so 2x plus 2y equals 120. Here, down in this box, I'm going to solve for y. Then, I'm going to take this, come up here, and substitute it in for the y that we have in the area function. So now I have area as a function of one of its dimensions. It's going to be the x dimension. And then this one actually says maximize the area. Well, the previous one said minimize, and this one says maximize. So why would this one change to maximum? Look at your leading coefficient of your x squared term right there. That's negative. A negative leading coefficient does not give you a minimum. It will only give you a maximum because that's the top of the parabola. So we still do the same thing, opposite of b over 2a, which is negative 60 over 2 times negative 1, which is 30. So one dimension is 30. If you get a negative number here and we're talking dimensions of a rectangle, you know you did something silly because dimensions of a rectangle can't be negative. It doesn't make sense. So the x dimension is 30. And at this point, if you want, you can plug in 30 into here to find the area and you'll get the correct answer. But then you have to do 30 squared and 60 times 30, which are kind of big numbers. So I think it's just easier to go find y. So y equals negative 30 plus 60, which is 30. It just so happens that the maximum dimensions, the maximum area is going to be found by using a square. So we have x is 30 and y is 30. Those are our two dimensions, and these are in feet. And then this says what is the maximum area. So to find the area, we multiply the dimensions together and we get 900 feet squared because area is two-dimensional. Now if you look right here, if I would have plugged in the 30 into the area function, 30 squared is 900 times the negative is negative 900, and 60 times 30 is 1800, so 1800 plus negative 900 is still 900 feet squared. Alrighty, let's hope this experiment works.